what we do today is you will have access to some of these ASICs. One of these is shown here in this nice photograph with a magic rainbow, as Sebastian Schmidt just said. Of course, we're not going to be able to do any top-notch science today, but to give you some inspiration of what is possible with these analog circuits, with this BrainScaleS 2 ASIC, there's a list of publications that have been published. It's probably not complete, but it might serve as some inspiration. I want to especially highlight the second and the third publication here. They are kind of aligned with the content of today's tutorial. So the first one is a publication on training analog neuromorphic spiking neural networks to perform some machine learning tasks using surrogate gradients. And one very similar rule, learning rule, will be part of this tutorial today. It's called SuperSpike and is kind of related to the second publication here. And the third publication is on HX-Torch, PyTorch for BrainScaleS 2. And that is because today's tutorial, the second part of that, will be on how to perform matrix multiplications with analog neuromorphic hardware. There's a very nice publication on that in that list. So feel free to click through that. So as I said, we will kind of do two things. We have one half of the tutorial will be on spiking neural networks. We will have a look at a single neuron, how it behaves, how these analog neurons will, how they maybe differ from the simulation, and how they like, how to set them up. And the second part of that spiking tutorial is the SuperSpike learning rule, which will be implemented in Python. So quite easy. And the second half is on that matrix multiplication mode, but there's other people here that will tell you more about that, more than I can. As you probably have seen, we have a Jupyter notebook set up. It's available on jupyterhub.boii.eu. The link is also in the Zoom chat. Maybe we can post it again for everyone who arrived late. So if you click on that link, log in with your eBrains account, you should be able to start a server and see basically these folders, and then open the first one, the 0 welcome Python notebook, please. So there's now 52 participants, probably 10 tutors, so quite a good ratio of tutors to students. Again, if you have any trouble, please raise your hand with the Zoom reactions feature, and we will try to solve these in breakout rooms. Questions regarding the content, you can always ask in the chat or here directly by speaking up. So these 40 of you probably that want to execute something on these BrainScaleS 2 ASICs, we don't have that many ASICs in the lab at the moment. But instead, we are going to time multiplex your experiments on our hardware using a microscheduler called Quigledy. It is trying to optimize all your experiments to fit them, kind of to interleave them. And so you shouldn't really notice that, besides maybe a slight slowdown when the resource is blocked by an experiment. But what you don't have to do is you don't have to hold a resource and then free it again, not to annoy other people. So you can just continuously execute your Python cells in the notebook, and everything should be done in the background. If you have any technical issues, please raise your hand. Okay, so to check if you're set up correctly, I would now ask you to execute the last cell of this Python notebook, Jupyter notebook, by clicking into the cell and pressing Shift-Enter. And if you don't see anything, that is a good sign. So as you see, I don't have any output here for this cell, but it completed its execution, and that is probably. I see some of you show me a tick mark. That is awesome. So if that worked for you, you can maybe just show that using the reactions feature. That would be awesome. And if you have trouble, then just ask. Okay, so there's no need to hurry. You can always skip back a little bit if you let us know. But I will now move to the first experiment, or the first part of the tutorial, which is, and again, if you want to have your data persistent, you shouldn't use the read-only copy. I will do so because I don't really need that. I want to have a fresh state each time I do that. So let's now open the single neuron demo. It's also available in this first Jupyter notebook by clicking on the first link here. Okay, so in this part of the tutorial, you will learn how these analog neuron circuits on BrainScaleS 2 behave, and how to set them up. The first cell is kind of just some boilerplate code. We import some Python packages that, for example, includes NumPy, and we use, as you will later see, these Jupyter widgets to introduce some element of interactivity, and we use Matplotlib for plotting. But the important imports are probably these 4 lines. Here we import Pine. Pine is a domain-specific language to set up spiking neural networks in a simulator or emulator agnostic way. We provide a backend for that Python package. It's called Pine BrainScaleS 2, and this language this package will allow you to configure, to set up your network graph and execute experiments on the hardware from a very high level perspective. And the only other thing that remains here is we define a helper function to plot some data, to plot some membrane traces, that just to remove some clutter from Bilaudelle's code. Okay, so the BrainScaleS 2 ASIC, the one you see here, that one contains 512 neuron circuits, and we will now look at one of them. And for that purpose, we set up a very simple experiment. It will simply record the membrane trace, the membrane potential of one of these neurons. And for that purpose, we first have to set up a network, right? We do this, as I said, using Pine. So let's maybe start here from this line. Pine.setup tells Pine that we are now ready to set up our network graph. We can inject some configuration already in this setup call, as you will see later. But at this point, we just leave that blank. And then we define our network. And in this case, our network is super trivial because it's just a single neuron. We do so by using the Pine population. A population is a group of neurons with, in most cases, similar properties. And our group of neurons here is of size 1 now. So we just set up one population with a single neuron. And the second part of that definition is the cell type. And Pine supports multiple different cell types, for example, the leaky integrated file model, and it's then mapped to all the different backends. For the moment, we simply provide a custom neuron type, which is the HX neuron. The chip you have seen, the ASIC you have seen in this photograph, it's a BrainScaleS 2 ASIC, but it's called HiCanX, and that is why we call it the HX neuron. And to that neuron instance, you then pass all your parameters, and these parameters are hardware parameters. And for that, and to understand that, we should maybe tell you that each neuron, for each BrainScaleS 2 neuron, has roughly 2 to 3 dozens of individual parameters. Each neuron can be controlled individually. That includes 24 analog parameters, for example, leak voltages, the leak potential, or bias currents to tune your neuron to behave to certain time constants and so on. And then also a lot of digital control parameters that defines the behavior of the neuron in a bit more coarser way. Yeah, so what you see here is that we tell our neuron to have a leak potential. So this is the technical parameter for the leak voltage of the leak. The leak results from the IPython widget, right? So it's creating the slider for you, and that directly controls a bias, so a reference voltage on the chip. We have 10,000 individual analog parameters generated on chip to be able to configure all the neurons independent of each other. And this is how you control one of them. We also set a second parameter. It's the leak bias current, and that just determines the time constant of the membrane. Okay, so now that we have our population of one neuron, we tell Pine to please record the voltage of that neuron, then execute the experiment and plot our results. And this 0.2 is in milliseconds. So Pine doesn't use SI units, but it uses biologically inspired units, but we directly interpret them as wall clock time. So these 0.2 milliseconds, so this is in milliseconds, which is 200 microseconds, right? This tells BrainScaleS 2 to please execute the experiment for 200 microseconds. And this is also what you see here. So it runs for 0.2 milliseconds. This is not translated into the biological domain because, as you probably have heard from the talks of Johannes Schemmel and Sebastian Schmidt, we execute everything, we emulate everything at a speed up of 10 to the 3 or 10 to the 4, so 1,000 or 10,000 times faster than the biological equivalent. And when you now just drag around that slider, you see that the leak potential of that neuron really changes. You see there's a little bit of noise on that membrane, indicating that it's actually an analog circuit that does that. And so to be able to read that out and to display this here, we have to digitize it first. We do so using an ADC, an analog to digital converter on the chip. And this is why you have these weird units here. This is just the output code of the ADC. It's in arbitrary units. It shouldn't really confuse you. It's roughly the equivalent of 0 to 1 volts approximately. Okay, so if you have any questions up to this point or technical difficulties, let us know. I will just...
Sure. I mean, I increase the leak voltage and I see the membrane potential going up. I would have thought it were the other way around.
That's a good question. Thanks. I mean, if you have a look at the leak integrated fire equation, then you see that term, the current that flows onto the membrane is proportional to the leak conductance, GL, and the difference of the current membrane potential minus the leak potential, right? So it always tries to converge towards the leak potential if the membrane is not disturbed. So this is actually the correct behavior. That if you increase EL in the LIF equation, you also increase your resting potential. So this is completely according to the equations. So maybe you can so this is not a current into the membrane, but it's really it controls the resting potential. It's basically the baseline of the neuron, if you wish.
Okay, V leak is like the resting potential.
Exactly. Yes, it's EL in the LIF. It's the equivalent of EL, the reversal potential of the leak. Yeah. Okay, but that's actually a good question, and it segues into the next experiment, because a spiking neuron without spikes is kind of boring, right? But before we actually define a network topology and connect multiple neurons together, we simply, again, have a look at the same neuron. So we basically do the same thing. We have a population of one neuron, but now we set some more parameters. and again execute for 200 microseconds and have a look at the output of that neuron. And here we configure a leak over threshold configuration. We can change this by just moving down the leak potential. Okay, so now we have exactly the same behavior as above, but without a fixed without fixed y limit. So now you again see just a resting membrane with a bit of analog noise. Yeah, but if you now increase the leak potential, you will see that your neuron starts to fire because the membrane is continuously pulled towards the leak potential as above, but now that leak potential is above the threshold. So that leads to the situation that the membrane rises and rises, crosses the threshold, and is reset to the reset potential. We can tweak all of that here. For example, we can shift the threshold, and you see that the upper bound of these traces will simply shift. Now it's at 375. If I increase the threshold, it's at 450. Here, please note that these numbers you see here don't necessarily have to be on the same scale. For example, V leak and V reset do share a scale, but V threshold, you see the number is actually below the reset, but there's an additional shift. So don't be fooled by these numbers. Just have a look at your membrane behavior. This is kind of the ground truth. This is just the intricacies of analog circuit design, but for the end user, that is completely hidden, and you will see later how we do this. Okay, so you can set the 3 potentials, and you can also tweak this bias current for the leak term. The leak term is kind of a resistor, but in CMOS technology, it's a pseudo resistor that can be tuned, yeah. So if I increase that bias current, we will decrease the leak resistance or increase the leak conductance, and that leads to an increased firing rate. If I decrease that, you can really reach very slowly evolving membranes. There are some additional more parameters here, and you can in theory, not even in theory, you can practically reach extremely long time constants with these circuits up to 0.5 milliseconds and down to 0.5 microseconds. So you can configure these circuits in roughly 2 to 3 orders of magnitude. I mean, you can always also try to only change these parameters in a very small, with low increments, and you will see that this is completely asynchronous, right? So the trace completely changes, even if I only move these parameters a little bit, because it's not a simulation, right? When recording this neuron, this is asynchronous. So the neuron continuously, now in the lab, these neurons continuously fire, and you just have a tiny little view on that for 200 microseconds. But after these 200 microseconds, they will continue firing that way. So you kind of actually modify an electronic living system in the lab. Okay, so I don't see any questions that came up. So we can maybe just continue. As you saw, these circuits can be tuned, and you maybe also notice the analog nature of these traces, right? We have some noise on there, but there's one more thing to take into consideration when using these circuits, and that is that if you have a look at 2 neighboring neurons or multiple neurons on the ASIC, they don't necessarily have to behave in the same way. This is due to manufacturing deviations. So each of these neurons will behave slightly differently. This is called fixed pattern variation, and we can try to visualize this in the next experiment. So what we do here is we now have a population not of 1 neuron, but of 10 neurons, and we configure them with the same parameters, right? So we again configure a leak over threshold configuration, but now have a look at 10 of these neurons. And since the ADC we're using only has one channel. There's more to that. So we have two different kinds of ADCs, but here we are using a fast ADC, and that at the moment is able to record only one neuron at the same time. So to be able to look at all of these 10 neurons, we have to repeat our experiment 10 times. This is why we have that loop here. We tell Pine, and with that BrainScaleS 2, to record the neuron with that neuron ID. For that purpose, we use a population view, which is kind of a subset of a population, and tell it to record the membrane trace, execute the experiment, and plot it. And you see in your output that you actually have now 10 recordings, and this is what you get. Okay, and here you kind of see how these neurons all behave slightly differently. You see that in the reset potential, that is kind of shifted for all the neurons. The same for the reset potential and the leak potential, and also the time constant is slightly off between the neurons. I mean, this doesn't necessarily have to be a problem. Just recently, we have published a paper how this mismatch can be actually completely ignored if you have a suitable learning rule. So your network learns the task, including taking while at the same time taking care of these fixed pattern deviations. But in some cases, you simply don't want that. And as I said, for that purpose, you can tune each of these neurons individually to equalize the behavior between the neurons. This is what we call a calibration, and we will use this for the later parts of the tutorial. Okay, so there's also one Outlook part here where we now configure a network. I will not walk through this, but instead wait for a few minutes now to let all of you catch up, to ask some questions, because we will also talk about this in the next part of the tutorial. So I'm just going to quickly check if there is any questions. There's one by Henrik Mettler. The question reads, since the ADC readout is in arbitrary units, how do you distinguish whether something is a spike or noise? That's a good question. I mean, the ADC readout per se is in arbitrary units. That doesn't mean that we don't have a translation between these units and the actual voltages. We just didn't set it up here because it involves some more measurements. We have absolutely done that, but not for this setup today. This is why we only show these arbitrary units. I mean, I think it's depending on the experiment, it's probably quite easy to distinguish noise and spikes. If you, for example, have a look at this trace here, I think it's quite clear what a spike is and noise is. So that should be on a completely different order of magnitude, right? You always see your spike when the neuron is reset to the reset voltage. But still, it's it really depends on the configuration. But I think in all typical configurations, you really have a quite large signal to noise ratio. This is what the signal to noise ratio basically determines how large the signal on your analog circuit is compared to the amount of noise you have. And as you see, in most cases, this is really rather respectable for these ASICs. So we don't really have an issue with noise that we don't want in these kind of networks. It depends on your configuration. If you move to extremely long time constants, then you basically don't stabilize your leak potential as well as you see here. So if you have a very long membrane time constant, that will amplify noise. That is something to consider, but it's practically not a really problem, right? So there's another question or another part to that answer by Sebastian Schmidt in the Mattermost channel. I would like to encourage you to also join the Mattermost chat for some more long-term communication. And there's another question there from Daniel Schmidt. It reads, does BrainScaleS 2 provide as well other neural models such as Izikowicz or ADEX? yes, you are looking at an ADEX neuron. It's just hidden, right? The LIF model is a subset of ADEX, or rather, ADEX is a superset of the LIF equation, the exponential terms. But this is something we provide. These are fully functional ADEX neurons. We are able to reproduce, I think, all of the now firing patterns in a quite nice way. So that is, yeah, that is completely possible. Okay. Great. If there aren't any questions anymore, I would like to continue with the next part of the tutorial, which is the Jupyter notebook called SuperSpike. This will be a bit more theory heavy, but yeah, if I'm too slow, just let me know. So you have already seen that we can configure and tune these neurons, but now we want to actually define a network, and we also want to train this network to perform some task. Here we don't really solve any real task. It should be a more educational. It should be a more educational example, yeah. So maybe some of you have heard about these surrogate gradient methods to train spiking neural networks. The idea here is that we want to perform a gradient-based optimization on these SNNs, and that is kind of hindered by the fact that these spikes are these binary things. The activation of a spiking neuron is a theta function, step function, and that first means that the derivative of that is a delta function that is very sparse in time. So only at specific points in time we actually have a gradient for a spiking neuron, and that can be circumvented, especially if you have some homeostasis term. If your network produces a lot of spikes, then that is solvable. But still, if you want to introduce spikes at specific points in time, that means that you have these critical points where the neuron just barely doesn't spike, or just emits a spike just by crossing the threshold very shallowly, right? So these critical points are something that are kind of hard in training these networks. And for that purpose, you can smear out the gradient, this delta function, to some arbitrary smooth function. So we don't modify the forward pass. We still have a spiking neuron with a theta activation function, but when kind of calculating the derivative of that, we just use a different function. This is what we call it a surrogate gradient. And there are some different methods for that. You can do so in brute force backpropagation through time setting, where you optimize your network using a auto differentiation framework such as PyTorch or TensorFlow. This is, for example, what we have done in a recent publication together with Friedemann Zenke. We just published that or updated the manuscript to include some more information for NICE on Monday. So it's on archive now. Here we actually train networks on hardware to perform benchmark tasks such as MNIST, or also with recurrent networks on audio data, the Heidelberg spiking digits. But this is not what we do here. It really allows you to get a lot of performance out of these analog circuits, and I think it's a pretty cool experiment. But here we do something different, and that is a forward integrated version of that. So the problem with these backpropagation through time approaches is that you really have to unroll your whole forward pass backwards to estimate all the gradients. And instead, you can do something that Friedemann Zenke published. It's called the SuperSpike learning rule, where you simply derive a numerical expression for the gradients and perform them and calculate the weight updates during the forward pass. So it doesn't introduce any more complexity. Similar things have been done by the group of Wolfgang Maas, namely Guillaume Bellec. He did that for recurrent networks, but these are very similar schemes where you just change your derivative, you approximate a derivative for the backward pass, and then derive a numerical expression. I hope I got that right. Please refer to the original publications to learn more about that. So here we want to now implement the super spike learning rule enough with the theory. We again import some stuff, including Pine. Define helper functions for the plotting. And then we can go on and configure the network. At first, we just set up some arbitrary parameters. For example, the number of inputs to the network. We just use 60 here. Again, the duration, as in the previous experiments, we use 200 microseconds, which, if you factor in the speedup of BrainScaleS 2, corresponds to 200 milliseconds on these typical biological timescales. And then we do something that is not necessary for the forward pass. We introduce a time step. Everything that is emulated on BrainScaleS 2 is continuous in time. There is no time step. It's not a numerical integration. It's a physical model. These neuron circuits and all the other dynamics, they evolve continuously in time. But to be able to calculate the weight updates numerically, it's just very convenient to define everything on the grid now. So we just define that at 0.1 microseconds, calculate the number of steps, right? And then define a time axis and bins. And these bins are required for generating your input spike trains and also resampling the membrane later for the learning rule. Not for the emulation, but for the learning rule. Okay, so now we can set up the network graph. And you will see there's kind of a weird part at the beginning with something called a COCO. And this is something that is not inherent to the Pine API, but it's necessary to calibrate the BrainScaleS 2 neurons. As you have seen in the previous part, these neurons do have some deviations in between them, and to get rid of these, we perform a nightly calibration for all the setups in the lab, and we just load one of them here. So we get the nightly calibration path for your personal setup, load these things called COCOs from this file, and then split these COCOs into general COCOs and neuron COCOs. A COCO is a coordinate container list. So it's basically a list of addresses for configuration registers on the hardware. These we call coordinates. And then containers, and these containers contain the configuration itself. So it's a list of configuration data and addresses that tell the backend where to write these configuration data. And we have a lot of configuration registers that are global, that influence the whole chip. These are general COCOs here. And then we have individual neuron parameters. These are the neuron COCOs. And these general COCOs we use in the Pine setup call. It was blank before because we didn't use that calibration, but now we do. And we just inject that configuration. So this is kind of a more low-level API that looks maybe a bit confusing to you, but because it's not directly available in the Pine API, but this is, I think you can simply copy and paste this. And good question by Daniel Schmidt. By having nightly calibrations, does this mean if I run a simulation in the morning, my results are cleaner than in the evening? Not really, no. It's more like a consistency check for our side. And if we deploy improvements to the calibration, that could mean that from one day to the other, you will have better results. But in theory, these calibration runs should result in very similar configurations. Okay, so now we have set up Pine, injected our calibration data, and now we can configure the network. Again, a good answer by Sebastian Schmidt. If you really have an experiment you want to do science on, you should always use the same software state and the same calibration data to get your results, because in some cases, you don't want to depend on the changes other people introduce, right? So you can freeze your state, basically. I could, for example, generate my own calibration. This is what we typically do if we have particular targets. So here we have, for example, 10 microseconds membrane time constant and 5 synaptic time constant, something like that. I'm not quite sure, actually. But if you do your experiment and you want, for example, 20 and 2 microseconds, you would generate your own calibration data, and that wouldn't change overnight. Okay, so now we can define our network. We, again, have a population of 1 neuron. We simply want to train a single neuron here. And instead of giving all these parameters individually, like we have done before, we now load these nightly calibration data using the neuron COCOs. And again, we tell Pine, please record the spikes and the membrane potential of that neuron. But now we want to go beyond that, and we want to actually have a network of these neurons, right? So we set up a population of spike sources. So you see this call is basically exactly the same as that one above, but we have not a single neuron, but n inputs. That was 60, by the way. And we just defined a different neuron type. And these are spike sources that have arrays for the spike time. So you can set them from Python. There's different kinds of spike sources, Poisson spike sources, but we do this manually here. And to connect these two populations, the input population to the output population, we define a synapse, kind of a synapse type. It's a static synapse. It doesn't learn intrinsically. We modify the weight from Python. This is what we call an in-the-loop training. But it doesn't change its weight continuously by some hardware means. There's experiments on that. We have these on-chip processes that you can use to implement learning rules, but this is not what we do here. And then we define two projections. A projection is like in neurobiology, which is not really my field, just a kind of a coarse view of a connection between one area of neurons of the brain to another area. And here it's a connection between, or a projection between two populations. So we define a projection between pop input and pop output. And we just say, please connect all neurons in these populations, in the input population, with all neurons in the output population. This is an all-to-all connector. There's also, for example, a fixed probability connector where you say, I want to connect 0.5, so 50% of my input population to 20% of my output population, and then it just has a sparse matrix, basically. We tell it to use a synapse, the synapse type we have defined before, and then we do that again. So this call is basically the same as that call, with one exception. The first one is an inhibitory projection, and the second one is an excitatory projection. And we do this because these projections kind of have Dale's law implemented. So since we, in this experiment now, want to have a signed weight, we have to define both parts of these signed weights. We have to define the excitatory component and the inhibitory component. And we will kind of circumvent this in the next Python cell. Here we want to work around Dale's law. This helper function takes a signed weight matrix of weights, clips it to the range of the 6-bit synapses on hardware. So each synapse has a 6-bit weight, but in addition, now we have two synapses, an excitatory one and an inhibitory one. So it's kind of a 7-bit signed synapse. And then we split our weight matrix into an excitatory component and into an inhibitory component, and then configure these two projections to have these two components. And these two components are kind of mutually exclusive. So if you have a positive weight, that means that you will have a entry in the positive weight matrix WEXC. If you have a negative weight, that will again be a positive entry in the inhibitory weight matrix. But that is just the internals. For you, now we have signed weights. So we can define that helper function. And now define Poisson spike trains. And we do this by simply calculating a Bernoulli process on a kind of a dense vector of time bins. So we have defined these time bins before, these number of steps with this arbitrary time step. So we now do calculate these input spike trains on a grid of 0.1 microseconds. We simply define an input frequency. This is per unit. These 10 to the 3 hertz are 10 kilohertz. And here again, please remember that speed up factor of the hardware, 10 to the 3. So in biology, this would be 10 hertz per presynaptic neuron. Then we calculate kind of the probability for a neuron to fire per each time bin. Oops, that part here. And compare that to uniform random data. And this is now a dense representation of our 60 input spike trains. Since Pine doesn't want to receive these dense representations, but a sparse one marking the points in time where a neuron spikes, we simply convert it to that. So these input spikes, we can maybe simply print this now, input. Sorry, I'm a bit slow to type now. So this should be 60 entries long for the 60 spike trains. And if we have a look at one of these spike trains, for example, 42, you see there's one spike for that unit at, this is again in milliseconds, Pine wants milliseconds. This is at 45 microseconds into the experiment. Maybe another one, 2 spikes at 65 microseconds and at 105 microseconds. Okay, now that we have the spike train, we can actually start to stimulate our target neuron with these spike trains. And what you see here is that at first we fix a seed. We want this to be reproducible, and you see it really is. Despite the analog nature of the circuit, this is really rather reproducible. So we draw a random weight matrix, set these weights using our helper function, execute the experiment for 200 microseconds, defined above, retrieve the data from Pine, and plot the membrane potential. And we do this first to see how this neuron now behaves. And second, we also use it to define a target spike train for the network to then later learn again from a different initialization of the weights. This would now be a rather hard task because we would have to reproduce a lot of spikes. This would mean slow convergence in the end. So as is written here, you should tune this now to get roughly 2 to 3 spikes maybe. You can do this by either changing the input frequency. So for example, if I go down to 1 hertz per unit and execute this, this is maybe also an educational view. So now you see that we have a lot, very low dynamic range now, but you really see the individual PSPs. We can also increase the weights. So this look now basically the same, and you see the neuron spikes now. Again, the lower your number of input spikes, the harder the task is, and to have a quick convergence in this context now, maybe just keep this at 10 kilohertz per input neuron, and instead tweak your weights such that your membrane emits roughly 2 to 3 spikes. Okay, you can play around with that. You can also redo this later and simply redefine your targets and train the network to different targets. I will simply use, okay, that is a very simple task now. Okay, that looks nice, 2 spikes. That should be easy to learn. And one more thing before I actually explain the learning rule now. These arbitrary units, or LSB would be the technical term, these are kind of arbitrary, right? As the name says. And for these numerical computations we now want to perform to implement the weight update rule, we want to have it normalized. That it would be the easiest thing. So we normalize this now to a range of 0 to 1. This is what we do in the next cell. So we simply extract the maximum and minimum of this trace and now redefine everything from 0 to 1. This is also required for the super spike learning rule using these surrogate gradients. And we can now do a very quick dive into that learning rule. So the idea here is that we want to minimize a loss function. And for spiking networks, one of these loss functions would be the Van Rossum distance. The Van Rossum distance tells you the similarity of two spike trains. And for that purpose, we define these two spike trains, Si of S. S would be the time now in this integral. S is the spike train actually emitted by your neuron, and S hat is the target spike train. And we perform a convolution with a alpha kernel, kind of the PSP kernel, but this is a bit arbitrary. You could use Gaussians here to avoid the use of delta functions in these spike trains. So you now have a smooth representation kind of your spike trains, and you simply subtract them in the time over time, right? So you have the difference of the convolved target spike trains minus so you have your convolved target spike trains minus your convolved output spike trains. You calculate the square because you want to have the absolute deviation from 0. And now the task is to simply get this to 0 as close as possible. We integrate over the whole time frame, and then we have a scalar loss, and that is what we want to minimize. The stuff here in these square brackets is what we call the error trace. It's E of S, E of the time. It's kind of the time resolved Van Rossum distance. And what Friedemann-Zenke published in his publication is that you can find a numerical solution to that loss function, or an approximation at least, to actually perform the weight updated calculations during your forward pass. We do this here now. So the weight update basically is basically a 3-factor Hebbian learning rule. This is kind of a Hebbian term. I will go into more detail now. And the second part here is the error trace we had before. And for each point in time, we calculate that product of that Hebbian component and the error trace, calculate the integral over the time frame, for example, the whole experiment, as we do now. And this is then the weight update between the presynaptic neuron J and the postsynaptic neuron I. And the Hebbian term is not really an STDP term. It can be approximated by that, some experiments suggest. But here we use the surrogate gradient that I have talked about before, kind of an approximation of the gradient of the membrane potential, sigma prime, and we will define that function later. And that sigma prime is kind of a smoothed out function of the membrane potential. If the membrane potential is at the spike threshold, that the output of sigma prime is simply 1. If it's far away from the threshold, that number is lower. And this here is basically, so this eta kernel in that convolution, epsilon is an exponential decay. So we simply have basically the exponentially decaying synaptic currents originating from the spike train emitted by presynaptic neuron J. And the product of this is kind of an eligibility for the synapse between J and I to receive a weight update, and it's modulated by the error term. This can be done for multi-layer networks. Here we do so for a single output layer, so no hidden layer, and we simply want our neuron to replicate the spikes emitted in the previous experiment. So let's now define this surrogate gradient function. We call it super spike. And we can also plot it here. It has a parameter called beta. It's the steepness, and it's basically what you see here. So steepness is, if you have a high beta, you have a very steep gradient. That means that you converge towards your delta function, basically. And the lower beta is, the less steep your gradient is, and the more you take into account lower values of the membrane potential. Okay. So you have seen that this learning rule now involves a few kernels. The first one is this epsilon. It's the exponential decay of the synaptic currents, and then alpha, which would be the PSP shape, and also the kernel used in the van Rossum distance. And that we simply have to define. These membrane and synaptic time constants approximate what you get from the nightly calibration you have applied, and then you can construct these kernels. These are simply exponential. So this PSC kernel postsynaptic current is epsilon, basically. And that is the exponential decay, and alpha and PSP is basically the alpha kernel, and that is the PSP kernel, the difference of exponentials. So it's basically the two low-pass filters applied. First, the low-pass filter of the synaptic currents and the low-pass filter of the membrane. And we use the same kernel we use for the PSPs for the van Rossum distance. Okay, let's define that, and we can now implement our learning rule. So it's basically, we use the network graph above. We again use our run function. Before that, we set the weights. And these weights, we now again randomly initialize because we don't want to start from the solution, right? So we set these weights to a random initial value, and then train our network for a few epochs. Here we define 30 epochs. We have a learning rate eta of 20, and the steepness of the surrogate gradient beta is just fixed at 5, and you can play around with that. For each epoch or for each trial, our data set consists of only one data point. So it's an epoch is one batch of one input, one stimulus. So we set the weights, execute the experiment, retrieve the data from our network, and specifically the spikes and the membrane potential. Now we resample the membrane because the time steps by the ADC on hardware are not necessarily completely equidistant, and we also don't need the resolution of that ADC, and it would just make our calculations more expensive. So we resample that to our time step delta t. We have defined this time axis before, if you remember, but it's basically the same thing but at a lower time resolution. Pine reset tells Pine that we have ended our experiment run, and then we basically just have to define the weight updates. Before that, I want to answer Henrik Mettler's question in Mattermost. Does, for example, tau mem equals 10 to the power of 6 mean 10 microseconds in the emulation and 10 milliseconds in real time? It depends on, I think yes, it's 10 microseconds. For us, real time would be the walk clock time, so really 10 microseconds. So the hardware in the lab now has a time constant, a membrane time constant of 10 microseconds. But it would be 10 milliseconds in your typical biological experiment. That is correct. So when we now want to implement the weight updates, we first have to calculate the van Rossum distance, the time-resolved error trace. We do this by binning our spike trains, first the spikes emitted by our network, or by our target neuron, to the bins we have defined before on our time axis, and we do the same for the target neurons. Target spike trains. So this is now a difference of two dense representations of spike trains. So it's 0 or +1 or -1, and we calculate a convolution with the kernel for the van Rossum distance. Then we plot our membrane trace and the error trace and go on calculating the weight updates. And this is the numerical representation of the formula you have seen above. This is really this integral. You see, we first take calculate the surrogate gradient of the membrane potential, multiply it with the presynaptic currents, or the postsynaptic currents, sorry, perform another convolution that falls out of the optimization of the van Rossum distance, multiply by the error trace for each time step, and then integrate over the time steps. And this is what you see here. We calculate the surrogate gradient, multiply by the eligibility, which results from the input spike trains and the convolution with the exponentially decaying kernels. Calculate the product of that, perform the convolution, multiply with the error trace, van Rossum distance, and simply perform the integral to calculate delta W, and in the end, update our weights with delta W. And now the fun part, sorry for all the theory, now is seeing our neuron to converge, right? So you see it started from ridiculous initial conditions, and it really learns to reproduce these spike trains, or hopefully learns to reproduce these spike trains in a targeted fashion. And you should see how it really nicely learns that. Again, this task becomes harder the more target spike trains you have. This just means that it will converge slower. And most notably, you see now we kind of almost hit our target after 30 epochs, not perfectly. But if you now have a look at the membrane trace, that is completely different from the membrane trace when we defined our target spike trains, because we initialized our weights in a completely different way. So we don't optimize on the membrane potential, right? The membrane potential is completely arbitrary to the loss function. The only thing that counts is that we want to hit our target spike trains. So this didn't really work out perfectly, only approximately, but I think it's still a nice example. What you can also try, you can always stop your execution. What you can also try is to have a silent membrane at the beginning, so a mean of 0, for example, and some standard distribution to your weights, and you will see that despite you don't have any spikes, and despite of the absence of regularization terms, due to the super spike learning rule that factors in these subthreshold data, the membrane potential, it really starts to converge towards the target spike train quite nicely. So I think this was quite a lot to wrap your head around. So I think I will just simply give you some time also to ask some questions while you can maybe play around with different parameters. So we formulated some exercises. You can use different target spike trains, or by modifying the weight, for example, in the cell above where you generated these target spike trains, you can change the input firing rates and so on, play around with the hyperparameters such as beta. For example, as we saw, if you increase beta, you will move away from that surrogate gradient. You will converge to the delta function. So we can try this now. We can simply say beta is 100 or something, and you will see that the network will not really learn because it doesn't have the data of the membrane potential, because it simply uses a very tiny window around the threshold to factor in. So this will learn, but in a very slow way. So this is definitely not the optimal implementation, but yeah, you can simply play around with that and ask some questions if there are any.